So hello and welcome everyone to this month's webinar on using pseudo-wells and the associated synthetic data created in SynthRock for rock property predictions using the machine learning plugin of the OpendTect software. So to showcase this functionality, we have a project from Onshore Canada where the objective is to characterize an unconventional shale gas play. This project contains a full stack seismic volume as well as a number of angle stacks. It also contains 4 wells which intersect the seismic survey. And in addition, we have a number of horizons. For example, this top horizon, which is called Musqua, is the top of the shale gas reservoir. And this horizon that you see in 3D is the base of the unconventional shale gas play. And the average thickness of this shale gas reservoir is around 120 milliseconds, which is essentially the two-way time thickness between these two horizons that you see on your screen. Now, in order to characterize the play, we do have access to a number of logs in these 4 wells. And we have various logs available, as you can see in our newly developed well data manager spreadsheet here. So we have the 4 wells, well A, B, C, and D, and a number of logs are available across all these wells. In principle, we can use this well data to train machine learning models which can learn relationships between seismic and a relevant target log property. However, in practice, it's quite difficult to create a good quality machine learning model to make such a prediction with only 4 wells. And this is a situation where the stochastic module of the SynthRock plugin comes in very handy. In that module, you could easily create a large number of pseudo-well models and the associated synthetic seismic response. And these 2 data sets you could use to train various machine learning and deep learning models in the machine learning plugin. And this is what I'm going to show you in next few minutes. All right, let's close this well data manager spreadsheet and head on to the SynthRock plugin, which you can access by going into the top analysis menu. From there on, you move on to the layer modeling SynthRock. The SynthRock plugin contains 3 modules, and we are going to use this top module called Stochastic Module to create a large number of pseudo-well models that are stochastically generated. These pseudo-well models are nothing but a representation of the subsurface, which has not been seen by available drilled well data. And this slide here talks about pseudo-well generation methodology in a bit more detail. So to generate pseudo-well models, all you need is some geological knowledge that could come from regional data sets or from analogs or from outcrops. And essentially, that is something that you need to define a stratigraphic framework, which essentially tells the program what formations are likely to be present in the subsurface and in what order, plus what lithologies are likely to be present in all these formations. In addition to this, you need some information from drilled well data, if available. The information could be from logs, tops, or well markers, or from core data. And the beauty of the SynthRock program is that the well information need not be within the seismic volume. You could also use information from nearby well data as long as the underlying geology remains similar. Now, you use the well information primarily to generate rock physics models, which essentially contain rock property distributions, or I shall say contain information about rock property distributions and their interrelations. Plus, you use this information in the program to create some statistical distributions. Essentially, when you combine these two pieces of information within a subsurface model, this model thereafter allows you to generate a large number of pseudo-well models, which essentially just look like any other well. The only caveat here is that these models, obviously, they do not exist in reality, and they are essentially a representation of an undrilled point in the subsurface. And here in this example, we see a few pseudo-well models which have a modeled acoustic impedance log shown. So let's move back to our stochastic simulator. And here, I already have a number of saved simulations which can generate a large number of pseudo-well models. So we go here in this bottom left corner to open a saved simulation. Let's start with the demo one. So this simulation has generated on the fly 300 pseudo-well models, which you can see here in this bottom part of the display. And on the top, you see the corresponding synthetic seismic from these pseudo-well models. Right now, what you're looking at is acoustic impedance log information. You can also look at other rock property information, or rock property logs, I shall say, of these pseudo-wells. And these are all those rock property logs that you have modeled in this left-hand side stratigraphic section, which is the core of the program. So this stratigraphic section should contain all the relevant geological and rock physics knowledge that you have about the subsurface. In our case, we have a rather complex reservoir section which contains a number of formations. The topmost formation here, Fort Simpson, is sort of the overburden, and the topmost reservoir formation here is this Musqua formation, which is underlain by various other formations. And the deepest formation, which is still part of the reservoir, is called Avi Lake. Now, in each of these formations, we have to model various lithologies that could be potentially present in these formations within our subsurface area. So if we look at, for example, the topmost reservoir formation, which is the Musqua formation, we can see that it can potentially have up to 4 lithologies. However, we know from geological input that within our subsurface, this formation is likely to have only claystone and the shale high organic content lithology, which happens to be our target lithology here for developing this unconventional shale gas play. This formation contains information about these 2 lithologies in terms of their rock property distributions and interlinkages. And we have a number of options to provide that information. You could simply provide this information by means of specifying a range or a random distribution or some sort of mathematical formula which can link multiple rock properties. Or you could use probability density functions. Multi-dimensional probability density functions are probably the easiest way to fill in this information. However, these probability density functions require you to have a little bit of well data available. In addition to this, all you need is to specify the thickness distribution of the overall formation and also in what percentage of area it is supposed to be present within the subsurface. In our case, we have entered that as 100%. Because we believe that Musqua formation is present everywhere. All right. So from this demo simulation, we have generated 300 pseudo-well models. What we can do next is simply right-click here and save all these pseudo-well models into one file. I will call it pseudo-well set 1. And we save it. Similarly, once the models are saved, we can go to another simulation and open it up. Now, in this simulation, you can see that some of the bottom mid-Devonian carbonate layers are not present. Because this is the geological scenario it is representing. Again, we save all the pseudo-wells, actually 300 pseudo-wells that we have generated from this simulation. And we call it pseudo-well set number 2. Finally, we repeat the same process by opening another simulation, generating again 300 pseudo-well models and saving them into a third file called pseudo-well set 3. Now the objective here is to use all these pseudo-well models that correspond to various stochastic simulations as input for training machine learning models that can predict rock properties of interest. And to do that, we need to get out of the SynthRock plugin and head on to the machine learning plugin. Now, to access the machine learning plugin, we need to go to Analysis, Machine Learning. As you can see here, the plugin is categorized under various tabs. Each tab represents relevant tasks associated with wells, seismic, and seismic plus well-based workflows. So obviously, we are going to go into the seismic plus wells tab because we are working with both pseudo-well log data as well as the associated synthetic seismic. And we will click on the supervised regression synthetics from pseudo-well option and hit go. This brings us to a 3-tab window which allows us to extract the example data for training a machine learning model, train the model, and finally apply the model on real seismic data to create rock property volumes or to predict rock property volumes. So let's start with the extraction step. We click here, click on the select button, and we see that we have our pseudo-well set that we have just saved in the SynthRock plugin visible in this window. We start by selecting all the 3 pseudo-well set, click on next. Now here we can define what type of synthetic data we want to generate. So the simplest option obviously is to have a zero offset stack. In this case, I'm using a seismic wavelet which is extracted from full stack seismic. It's already been scaled to match the amplitudes of the full stack seismic. So I will give this volume, or sorry, this synthetic a name called full stack seismic wavelet. In addition to this, we can also generate elastic stacks, pre-stack gathers, and from them we can generate angle stacks, AVO gradient, etc. In this case, we are going to use this last attribute option, and we are going to generate a number of relevant seismic attributes. For example, amplitude, frequency, Hilbert transform, and perhaps this cosine phase one from the full stack synthetic data. So we now have 1, 2, 3, 4, 5 synthetic data sets which will be computed from the pseudo-well logs. In this case, obviously, the acoustic impedance log of the pseudo-wells. So we press next in the last step of data extraction, wherein we need to tell the program what are the input features and what's the output here. So the input features are the seismic, full stack seismic, or I shall say full stack synthetic data, and amplitude, frequency, Hilbert, and cosine attributes computed from that synthetic data. Now, as I mentioned earlier, our target here is to characterize a high organic content shale. So that rock typically has low acoustic impedance values. So one of the obvious targets here is to output acoustic impedance. In principle, I can choose multiple logs or multiple rock properties on the target side, but for this demonstration, I will limit myself to a single target, which is acoustic impedance. Further, I need to specify the log upscaling value, which is going to be 2 milliseconds, because the seismic survey sampling here in this case is 2 milliseconds. In addition, I'm also telling the program here to take not only the seismic data in front of a particular acoustic impedance sample, but also take into consideration 10 samples above and 10 samples below. This is essentially an indirect way to take care of the low frequency trend, which is quite common in well logs. In the end, I only need to provide a name for it. So I'm going to write something like full stack size plus attributes for AI. And all I need to do now is simply press on run, which will start the data extraction process. So the data extraction takes a few minutes, and at the end of it, the program will take you to this training tab, wherein you will see the example data visible in this top field, which you have just created from the pseudo-wells. And this example data, of course, contains the target AI log from the pseudo-wells, as well as full stack synthetic, and a few attributes computed from that full stack synthetic, which are the input features for predicting the AI rock property. Now, in OpendTect, you have access to a number of frameworks which allow you to use various deep learning and machine learning algorithms present in these frameworks to perform this model training. So for this exercise, we'll use the Scikit-learn library or the Scikit-learn framework, wherein we have access to a number of machine learning models or machine learning algorithms, from support vector machines to neural networks and various ensemble models such as random forest, XGBoost, and so on. For this case, we are going to use the XGBoost algorithm, which is an extremely fast gradient boosting method based on a base simple estimator decision tree in this case. You are going to use the default number of estimators 100. Maximum depth of each base simpler model, which is decision tree, we'll keep at 5. We'll only change the learning rate to 0.1. Now all we need to do is give it a name, XGBoost for AI prediction, and hit run. So you will immediately see this machine learning training log window appear, which currently is showing us that the data is being preloaded. However, as the XGBoost model is quite fast, the training should not take too long to finish. All right, the training has just finished, and the program shows that cross-correlation coefficient with validation data, which is essentially 20% of the entire example data set aside, is 0.93 almost, which is quite a good cross-correlation coefficient of prediction for acoustic impedance. Now the final step is to go into the Apply tab here and apply this model to a real seismic volume. We click on Proceed. And now the program asks us to specify real seismic volume and at various attribute volumes which are used in the synthetic mode to train the machine learning model. So we select full stack seismic here. For amplitude, we have already calculated an amplitude attribute volume from the full stack seismic. Now frequency, Hilbert transform, and a cosine phase attribute volume. Now I would like to apply the XGBoost model only on a single inline to speed up the process. And the inline that I'm going to choose is inline number 5505, which passes through the well A. Let's call it XGBoost predicted acoustic impedance. And we hit run. The processing of the model application has just started, and it should finish in a minute or so. All right, the processing has finished. We could close this window, get out of the machine learning plugin, and here we would like to display the results along an inline that we have selected for this quick model application, and compare the results with the acoustic impedance well logs of the well A. So here is the inline 5505, which passes through the well A. We are looking at the full stack seismic volume and the top and base reservoir horizons, as well as the acoustic impedance logs of this well A. So let's quickly load the predicted XGBoost predicted acoustic impedance along this line, and we see that the XGBoost model has done quite a good job to predict acoustic impedance property along this line that passes through the well A. As we can see, that we have a good match with the well logs, and these very light green colors corresponding to the lowest acoustic impedance values, they are representing the target high organic content shale lithology here, which is what we want to characterize. So just like acoustic impedance, we can predict any other rock property as well, which has been modeled in the pseudo-well set. So on your screen, you are looking at an XGBoost predicted Young's modulus property along this line that goes through this well A, and we can see that we have a rather good match again between the machine learning predicted Young's modulus and the Young's modulus log of this well A. The difference between the previous acoustic impedance prediction and this one is that for Young's modulus, we have used multiple angle stack volumes and a few attributes derived from them as input features, as opposed to using only the full stack sizing volume, which was the case for the acoustic impedance prediction. And these bluish colors, they correspond to the target high organic content shale lithology that we wanted to characterize. With this, I conclude the webinar. Thanks very much, everyone, for your attendance and your attention.